Hello my scholars, this is my school channel and my name is Abiola. For this video lesson, you are going to join me to tackle the JAMB CBT past question for the subject physics the year 2022. Do not go anywhere, stay with us and we will be right back. Welcome back to my school YouTube channel. So right here in this video we have question 1 to 20 to tackle. So let's begin with question number 1. So which of these is a derived unit? Units are what we use, to measure quantities. So we have fundamental quantities and derived quantities. So right here we're talking about fundamental units, units used to measure or units attached to quantities. And of course, we'll be talking about the units, the derived units used to measure derived quantities. So basic fundamental quantities, we want to talk about length, mass, and time. So the unit for length, right, is in meter, right? The unit for mass is in kilogram, and the unit for time is in second. Do you see that now? So I've just listed fundamental quantities and their units. So you can see that there's an exemption that we have in the option C, that is Newton. So force is a derived quantity and the unit is of course Newton. So because we have mass times acceleration, you can see, so there is a presence of two units coming together to produce this particular quantity, right? So definitely this gives us the concept of being a derived unit. So Newton is a derived unit for a derived quantity which we named as force. So the unit for force is Newton. So option C is the correct option. Question 2. A bar magnet is divided into two pieces. Which of the following statements is correct? So you want to recall this, right? A magnet, every molecule of a magnet still retain their magnetic property under normal conditions, of course. So when you now divide a magnet, right, into two, of course it's still going to retain its magnetic property, right? So that is going to have the two poles, the north pole and the south pole. So when we have this kind of scenario, a bar magnet being divided into two pieces, what is going to happen? What's going to happen is that the magnetic field of each separate piece becomes stronger. This is incorrect, right? The electric field is created. No, this is not good. The bar magnet is demagnetized. This is wrong. So the correct action that we should have or result that we should get is that two new magnets are created, and these magnets, they have their individual poles, right? So the first magnet, is going to have the north and the south pole. Then the other magnet as well, we have its own north and south pole. So we have two new magnets are created. So option A is the correct option. 3. Consider the wave equation y equals 5 mm, right? Sine, we have 1 centimeter, we have raised to power 1, then we have x minus 60, x raised to power minus 1, then t. The wave number is what? All right, so I intentionally pronounced all of this, including their units. All you just need to do is just to recall the wave equation, right? So this is your A, right? Remember that your A sine, then whatever we have in the parentheses, right? So this is for your amplitude, this is your A, right? Then you now recall we have that thing that looks like W, that's your angular velocity, and T. So you can see this is it, then the T, then we have Kx. Now the K is the angular wave number that we are looking for, then the X, the horizontal displacement. So you just need to record the formula, then you slot in the values provided right here. So what represents the wave number here? It is this, the 1 centimeter raised to power minus 1. So where do we have that presented? We have that packaged in option C. So option C is the right option. Question 4. An object 40 centimeter high is 30 centimeter from the pinhole camera. So if the height of the image formed is 20 centimeter, what is the distance of the image from the pin height? Okay, basically from the pinhole. So this is what we are going to resolve, right? So you just recall your formula regarding magnification. If you have your this image height, object height, then image distance, then object distance. So this is exactly what we are looking for, right? So we just have this equals, this and this come together, right? Sorry, we have my hi, right, multiplies my object distance, okay, then over this. So basically, what are we supplied for the value of our image height? We have 20, right, times the object distance, we have 30, then we have this as 40. The object height, you know, from the beginning of the question, we have an object 40 centimeter high. So we have this, you know, this cancels this. So I have 4 here 1, 4 here 5. 5 times 3, I have 15 centimeter. So this is the value of what we are looking for. So let's run a confirmation together on the screen. All right, so we have option A. So option A is the right option. 5. A bar magnet is placed near and lying along the axis of a solenoid connected to a galvanometer. All right, so the pointer of the galvanometer shows no deflection when what happens? All right, so the deflection we actually notice on the galvanometer is due to the presence of electric current, right, in the coil. So right now, when there is a movement, right, relative motion regarding the magnet and the solenoid, right, you are going to notice a deflection. You know, that movement can be that the magnet is moving towards, you know, the coil, or is moving away from it. So that movement will not influence a deflection, right, in the galvanometer. But when there is no deflection, that tells you that there is no movement, right? So we're basically talking about relative motion of the magnet and the solenoid. All right, so this happens when there is no relative motion, right, between these two items in the setup. Right, so let's see the option that actually tally with this. You know, when the magnet is moved towards stationary solenoid, this is incorrect, right? When it is moved towards it, of course, you are going to see a deflection, right? When there is no relative motion, that is when you see that there's no deflection, right, regarding the pointer of the galvanometer. So B is correct. The magnet is moved away from the stationary. So when the magnet is moved away, you will notice deflection in the opposite direction. Do you see that now? So solenoid is moved away from the stationary magnet. So the correct option is option B, right? The pointer of the galvanometer shows no deflection when there is no relative motion between the magnet, the bar magnet in this context, you know, and the solenoid. So option B is the right option. 6. Tires are threaded to do what? All right, they are not threaded so that you can increase the weight of the tires. No, we don't do that. We don't thread tires, you know, to increase its longevity. Okay, so contrarily, you know, when you thread tires like that, you know, you are increasing friction, and that leads to wear and tear. Okay, so tires are threaded to look good. Of course, it gives it a nice look, right? But that is not the purpose. It's not about aesthetic, right? It's about functionality. So when we tread tires, you want to increase friction, you know, especially during rainy season, or you have a wet path, you know, to tread. So you need this treading, right, on the tires so that you can have a firm grip, and you know, that is where friction comes in. So the treading on the tires are actually to increase friction. So option B is the right option. Number 7. A car starts from rest and covers a distance of 40 meters in 10 seconds. All right, so calculate the magnitude of its acceleration. So what I'm required to do, you just have to pull up a formula, you know, that carries all of these parameters supplied, and the one required, of course. So we look through the equation of motion, then we went for this, right? S equals to ut plus half at squared. So if you look at our given data, we're told it starts from rest. So that tells you that the acceleration, you know, that's starting velocity. Initial velocity is actually 0. The acceleration is unknown. That's what we are looking for. Then we have the time used, that is actually 10 seconds. All right, so we just have to slot this in. So I have my S as, the distance covered is of course 40. Okay, I told 40 meters. So I'm going to put 40, right, equals, this is 0, right? 0 times whatever value is here, that's gone, right? So basically I have half times A, right, times T squared, that is 10 times 10. Okay, so I have my 2 here 1, 2 here 5. So basically I have 40, right, equals to 50A. 5 times 10, 50 times A, higher 50. So what do? Divide both sides by 50. 4 divided by 5, that should give me 0.8. No, we are dealing with acceleration, that is meter per second squared. All right, so that's our answer. So some presentation will give you something like this, meter per second square. This is what this means. M times s raised to the power minus 2. You know, if you recall your indices, right? 1 over s raised to the power 2. You can see the same thing. So that's why we have per, or m over. So if I bring this, I have m over s raised to the power 2. So this is what it implies, just the same thing. So in case you are given this kind of question, right? So let's go back to the box. We run a confirmation for our value 0.8. Yes, of course, we have 0.8 in option C. So option C is the right option. Don't forget that you can actually have a JAMB simulated CBT experience before your actual exam. So all you just need to do is to click on the link in the description below. This is going to get you to the Myschool website. So right there you get to download the Myschool mobile app for your Android devices, or you can go for the Myschool software for your laptops and other computers. So join me as I tackle question number 8. The relationship between the coefficient of linear expansion, which is represented by alpha, and volumetric expansion by gamma is what? All right, so when you talk about the types of expansion, we know we have linear expansion, right? We have the area of superficial expansion, then we have the volumetric expansion. So basically your linear expansion is actually like your area expansion, which is the number 2, is like 2 times of this. Right, then for your volumetric expansion, that is 3 times of alpha, right, which is what I have here, 3 times of your linear expansion. So the volumetric expansion is actually y, or let me just say y, or gamma equals to 3 alpha, so I have it right here. So if here I'm being asked what is my area expansion in relationship to my linear expansion, that will be what? Equals to 2 alpha. So area of superficial equals to 2 alpha. Then this gamma, which is volumetric, is equals to 3 alpha. So I have this represented. Yes, option C is the correct option. Please don't forget the like button. Also click on the subscribe button and do tap on bell notification for you to get informed immediately we upload the next video content. We have question 9. Which of the following is not a consequence of hydrogen bubbles covering the copper plate of a primary cell? So I'm going to take a simple primary cell right here. You know, you can refer to it as the voltaic cell or the zinc copper cell. So basically, we're looking at which of this option, right, is not a consequence of hydrogen bubbles. So basically, when you look at this concept of hydrogen bubbles, you know, covering the copper plate. So for a simple primary cell, you know, you have the zinc, right? We have the copper. You know, these are of course electrodes, right? So when there is a covering of hydrogen bubbles, right, what happens is that that is actually polarization. Okay, so this is of course the concept that well engulfs this. This that is well described here. Then we have option A, formation of hydrogen bubbles on the electrode. On what electrode are we talking about? We're talking about the copper electrode. So this is as well variable. Then if you look at B, increase in the resistance of the cell. Of course, you know, the flow of electric current, you know, through the external circuit, right? So this is going to cause a decrease, right, as there's accumulation of these bubbles. All right, so look at C, local action. Of course, local action also involves hydrogen bubbles. However, the hydrogen bubbles, they actually gather around the zinc, right, not the copper. So because of the essence of the copper plate that's been talked about, you know, with hydrogen bubbles, so the one that is not involved is actually this local action. So this should point to zinc, you know, to be very specific. So option C is good to go. 10. A cell whose internal resistance is 0.55 ohms, right, delivers a current of 4 amperes to an external resistor. So the lost voltage of the cell is what? So when you look at the concept of lost voltage, you know, you want to recall EMF, right, and terminal PD. All right, so basically for the lost voltage, the formula that you require is just your I, which is your current, times the internal resistance. That is the small r, and that's what we have here. So that is 4 times 0.55. That will give me 2.20 volts. So the correct option is actually option B. Question 11. Which of the following liquid is a poor conductor of electricity? So for a liquid, you know, water in this context, you know, to conduct electricity, you know, it requires ions, right? And for there to be presence of ion, you're talking about solutes. You know, sometimes you can refer to them as impurities. You know, these are actually what serve as the vehicles, right, of transmitting electricity or conducting electricity. So for a distilled water, you know, is the purest form of water, at least to put, right? So you've removed the solutes, you remove impurities, you know, you've removed vehicles, right, that will actually conduct electricity. So there are no ions for conductivity, and hence you are looking at a neutral substance. So there is no way that electricity will be conducted, you know, through this liquid. So of course, in tap water, you have the presence of some basic metallic ions, right? Probably like sodium, you know, your seawater, of course, salt. Remember your salt, right? It contains sodium chloride, basically. So you can see we have ions there, right? Then we have your drinking water. So basically, this is the purest form. You know, you have removed the vehicles for conduction. So option A is the right option. Number 12. An isotope has an initial activity of 120 BQ, right? So 6 days later, its activity is 15 BQ. So the half-life is what? So there are actually different methods, right? So I'm just going to use a simple one. So we have initial activity of 120, right? So then we now have this 15. All right, so we just need to look at, okay, how many times do we need to divide this 120, you know, to get to 15? So definitely we're talking about half-life, so that's divided by 2. So I have 120 divided by 2, that gives me 60, right? Then this 60 again divided by 2, that gives me 30, right? 30 divided by 2, that gives me 15, right? So how many times do I need to move, right, to get to this 15? I moved 1, 2, 3, right? So that would just be 6 days later. So that will be 6 days, right, divided by the times I moved, right? This is it. So basically, each half-life, right, is actually 2 days. So where do we have that? Option B. So option B is the correct option. Question 13. The secondary pigment consists of what? All right, so for you to be able to identify secondary pigment, it's important that you can identify the basic primary colors or the pigments in this context. So the basic primary, we are looking at red, blue, and green. So if you look through the options and you find any option containing at least one of these primary color, it disqualifies that particular option. So let's do a lookup. So I have blue, green, and violet. So the presence of blue and green nullifies these options, right? These are primary colors. So we have yellow, green, and magenta. So green disqualifies this option. Then I have magenta, yellow, and cyan. These, of course, are secondary pigments or secondary color if you want to put. Then we have red, green, and blue. These are actually primary colors. So the correct option is option C. 14. A person standing waist deep in a swimming pool appears to have short legs, right, because of light, right? So what has happened to light? That's actually refraction. You know, we can see its effects. You know, the swimming pool appearing shallower. You know, when you dip a stick into it, you know, it appears shorter, and so much effects like that. So basically, refraction is just changing the direction of light when it travels from one medium to the other. And of course, we're talking about transparent medium. So the correct option here is refraction for option B. Question 15. A turning fork having a frequency of 312 Hz emits a wave which has a wavelength of 1.10 meters. So we're asked to calculate the velocity of sound. So basically you just have to use your V equals to F lambda. Your F is for your frequency, then your lambda is for this. So this is 312 times 1.10. What are we going to get? We are going to get 343.2 meters per second. So the correct option is option C. 16. When the plate area of a capacitor increases, what is going to happen? Of course, we are going to be looking at higher voltage and as well an increase in the capacitance. So the correct option here, you know, without no further ado, is of course option D. So the capacitance increases, you know, as we have increase in the capacitor area, and of course we are looking at higher voltage. So option D is the correct option. Number 17. A magnet relay is a device used for what? So basically, you know, you want to actually manage, or we have the term control, control a larger electrical load, right, using small signal, right? So basically, you are just saying that we have larger currents being involved or larger voltage, right? Then you want to switch, you want to use a small switch, right, to run this control. So basically that is where a relay comes in. Just think of it this way, you know, look at the power being supplied, you know, coming to us, you know, as users. You know, we're using appliances of lower voltages. So basically you need a protection system. So that system, that is where the relay comes in. So it offers protection to us, right, using requiring low voltage. So basically it's about controlling another circuit carrying larger current. So that is where the relay comes in. So option B is the correct option. Do you have questions bothering you? All you just need to do is to click on the link in the description below. This is going to get you to the Myschool website. So right there you get to ask your questions and interact with our solution providers, you know, for the required answers. So join us as of question 18. According to kinetic molecular model in gases, so what we want to know is that these gas molecules are actually in constant and random motion. You know, they are always moving, right, and they collide with one another, and the walls of their container, you know, there's no specific volume, so they just occupy as much as space available in their container, right? Then again, we want to see that there's neither force of attraction or repulsion, you know, between them, and these molecules are very small and they are far apart. So looking at the concepts or the models I've quoted so far, so we can see that option C actually tallies. So we have the molecules are very far apart and occupy all the spaces made available to them. So option C is the right option. It is so much possible that you have better explanations to offer. Please, all you just need to do is to use the comment section below, indicate the question number and the explanations or solutions you'd like to share. Question 19. A current of 0.5 amperes flow through a resistor when connected to a 40-volt battery. Alright, so how much energy is dispatched in 2 minutes? So you just recall this formula, you know, energy equals to P times T, right? Where you recall that your power is actually your voltage, you know, times your current I, then we have times this T. Okay, let me just use a small letter. Okay, so what do I have? My voltage is actually 40, you know, times the current, which we have 0.5. That is still 1/2. All right, so you can use your 0.5. You can punch your calculator, you know, to boycott this long process. So then I have my time is actually 2 minutes, you know, times 60, converting to seconds. So basically I have 2 cancels 2, right? Then I have 40 times this. I should have 4 times 6, that is 24. Then I have 2 zeros, 1, 2. So I have 2,400 joules, please pardon me. So energy is measured in joules. So the correct option is option A, 2,400 joules. Number 20. For a pear-shaped conductor shown above, the concentration of charge on the outside is highest at where? So for this kind of pear shape, right, you know, maybe you want to talk about spherical shape, you know, right there in this concept, the charges are not uniformly distributed, that is, they are not equal, right, on that particular shape or on those shapes, right? So right here we have a pear shape. So where is it concentrated? It will be concentrated where it is sharply curved, you know, sharply curved. So where do you have that now? You know, from my demonstration, we have it at point X. So we have the highest concentration right here. So where do we have the correct option? We have option A. So option A is the right option. Right now we've come to the end of this video session. However, we still have more clips to come. Please do not forget to hit that like button, click on the subscribe button, and always tap on bell notification for you to get alerts immediately we upload the next video lesson just for you.